The May book does things for compact Lie groups, so it's a slightly more general setting, whereas the rest work with finite groups. And I think that, obviously, if you're looking for the more general thing, that's great. And if you want to think about some finite groups, then sometimes that can be a little bit more cumbersome than necessary. So I'm going to stick squarely with finite groups in this mini course. I almost called it a mini series. Okay, so maybe before I really dive into it, let me just say a little bit about why you might want to study equivariant cohomology. Probably if you're here, I don't really have to convince you, but of course there's this landmark paper by HHR, Hill, Hopkins, and Ravenel, proving the non-existence of manifolds with curvaire invariant 1. And essentially they use equivariant homotopy theory to take this non-equivariant problem and turn it into an equivariant one and solve it there. And so in general, having this extra structure around complicates things, but it also rigidifies things. So sometimes you can prove more with having that all there. There's also a lot of connections to motivic homotopy theory. So there's this Betti realization functor that goes between the two, and people have used that to push computations back and forth. And I would argue it's just interesting in its own right. I think that's my main motivation. I think equivariant homotopy theory is just kind of fun. And one of the reasons I think it's so fun is that there's a lot of low dimensional and classical objects that are really accessible and not well understood in the equivariant world. So say you take your graduate algebraic topology course and you're like, wow, real projective space was super fun. And then it doesn't tend to come up in algebraic topology research, at least in a lot of the research that I see, but in equivariant cohomology, that is actually something that's interesting to think about, and we will later on in this course. So anyway, I think all of that's kind of neat. So that's my intro, but now let's go ahead and get started. So let's scroll up here. Okay, and sometimes my thing wildly scrolls, so I apologize for that in advance. But as I said, I'm going to let G be a finite group for all of this. And the category we want to think about is the category G top. So this is a category with objects that are given by spaces with a G action. Maybe let's say category of spaces with a G action. So I've got some space and my group acting on it, and I want equivariant maps. And these should be continuous maps that are equivariant. So some map between X and Y should have that if I act and then apply the map, that should be the same as acting after applying the map, right? Okay, so I'm guessing that that's basically familiar to all of us, but maybe it's worth saying in case this stuff is new. So already you get some kind of interesting connections to non-equivariant stuff. So anytime you have a subgroup, H sitting inside G, then you get a restriction map. So that gives you a well-defined map on the fixed points, and it'll land in the fixed points of Y. Try to make that readable. Okay, so that's how we're going to define weak equivalences in this world. So some map F from X to Y is a weak equivalence. Well, we'll take as our definition, if you look at this restriction to the fixed set, and now those are, we could just think of those as non-equivariant topological spaces. And so we'll say that should be a weak equivalence. And let's do that for all subgroups. Okay, so this is a theme that comes up a lot, is that we kind of want to think about all of the subgroups of H, or sorry, all the subgroups H of G all at once. Okay, but as in non-equivariant homotopy theory, of course, I don't really want to think about all spaces. I want to think about nice spaces. So the nice spaces here are called GCW complexes. And I'll say these are formed by attaching orbit cells, but I'll make that more precise. So what's an orbit cell? I've got G mod a subgroup, that's an orbit, cross a disk. I can give this the diagonal action and I'll take dn, that disk, to be fixed. Okay, and essentially this is just my equivariant version. How do I soup up my CW complex structure? If you prefer, you could think about just CW complexes that have a cellular G action. That's going to be equivalent. But what do I mean by attach orbit cells? We'll attach them in the usual way. So via the usual push-out diagram with equivariant maps everywhere. And I'll actually write that just to make sure we're all on the same page. So the boundary of a bunch of these cells looks like a disjoint union of a bunch of G mod H cross Sn minus 1 maybe. And I would attach those to my n minus 1 skeleton by thinking about how that boundary sits inside these orbit cells. And then take the push out and form my n skeleton. Okay, so, and as I said, equivariant maps everywhere. Okay, so part of why these are the nice spaces to think about is that we have an equivariant version of the Whitehead theorem. By the way, I saw in the chat someone asked if the notes will be posted, and the short answer is I will try. So sometimes these files end up gigantic and I may have trouble getting it on the website, but if that's the case, then feel free to email me. I'll like zip them up and send them to you or something.
And Clover, there's another question about
yes, is it the same? Thank you. Is it the same H everywhere? So no, I'm being kind of sloppy. You know, I really should probably like index this as some H sub I and over some indexing set I. So I'm being kind of lazy here. Good question. But really there could be lots of kinds of orbit cells. We'll see that later I'm going to make, well, it doesn't matter, but I usually think about C2, the cyclic group of order 2, and we'll specialize to that in a bit. And then there aren't a lot of orbits to choose from, but there are still 2 kinds. So yes, I want to allow all of those. Okay, great. Okay, what was I writing? This equivariant Whitehead theorem says that a weak equivalence between GCW complexes is actually a homotopy equivalence. Okay, so that just tells me that these are kind of the nice things to study, and there's a bunch of other stuff, especially in that May et al., the Alaska notes, that kind of sets up that, yeah, you have a nice category where a lot of nice things happen. That said, a lot of the things you would want maybe don't always happen. So we have to be a little bit careful. Okay, but once I have all of this set up, I can define homotopy groups. And I find out that I really should have a homotopy group for each subgroup. So if I had some equivariant space, I'd define pi nh of x. And this is maps from Sn to x. Well, really I want to take homotopy classes of H equivariant maps. So I'm going to decorate this with an H. And when I just write Sn here, I mean that this is fixed. So these are maps out of a fixed space. And since they're equivariant maps, that means they can only hit fixed points. So by adjunction, this is the same as non-equivariant maps into the fixed set. And that we recognize as the homotopy groups of the fixed set, XH. Okay, now I've kind of lied to you a little bit here. So part of what I want to do in this is kind of alert you to all of the things that are subtleties that people usually brush over and try to make those clear so that you don't get caught up in them. But I see a lot of things going by in the chat, and so let me hold off on that. So someone asked if you only attach representation cells, is that the same thing? And it's not quite, I think. Though actually, I'm not sure that I'm parsing this correctly. So let me say that there are representation cell complexes that are kind of a special type of complex we'll come back to later. But I do think there's a way to sort of define these DNs as D of a representation and then just like the unit disk in a representation and not really care about that action and sort of shuffle it away so that it ends up being the same. But, oh, someone caught me in the lie. So here I had to take X to have a G fixed base point. Yes, so that was exactly the issue that I was about to address. And before I do that, it's hard to look at all of the things, see you in the chat and all that stuff, so bear with me. But do we include maps that are not fixed by H, but whose homotopy class is fixed by H? So I'm not saying that the maps are fixed by H, I'm saying that they're maps out of a fixed space. And so if the, when I look at this equivariant, I could be misunderstanding this question. So if somebody sees that I am, please correct me. But if this is fixed so that this is just f of x, well, then I could also think of it as, f of my unit times x. And this needs to be g f of x, but it also then needs to be e dot, oh, I'm running out of space. Well, let me say you pull out the e and it doesn't do anything. Still got to be f of x. Oh, I already wrote that. So let me not write it again. But my point is that also has to be fixed. Okay, and then the question is, do they have to be equivariant maps or can they be equivariant only up to homotopy? And they should be equivariant maps, but then I want to take homotopy classes of those. Okay, cool. So yeah, so someone caught me in this lie. So really, whenever we talk about homotopy groups, we really are talking about pointed homotopy classes of maps, right? So these really need to be pointed maps. So I kind of set you on the wrong path. We shouldn't think about G-top. We should think about pointed G-top, where everything has a fixed base point. So an object in here is all of the stuff before, but also has, and not just an H fixed base point, but fixed by the whole group. So a G fixed base point. Okay, and this issue about base points actually causes sort of some headaches sometimes. I've spent way too long thinking about base points in this world, so that's why I'm making a big deal out of this. So for example, now I have this pointed G top, and G, one of my favorite G spaces, is not in this category, right? So that's an easy thing to fix. I'm just gonna write G plus, and I just mean give it a disjoint base point. But that's gonna come up anytime you have something with a free action, or maybe you were trying to think of it as an H fixed point, but not a G fixed point. You should really think of all your spaces with a G fixed base point. And sometimes we can be a little bit sloppy about that and forget, and it can cause some issues. So be careful. Okay, great. Okay, so with this category, these are the things we want to think about, but what we really want to do is compute equivariant cohomology. So Verdon defined an equivariant cohomology theory, taking into account the G action on these spaces. So I'll decorate it with a G to say that it's equivariant. And you notice pretty quickly that this N that I'm writing as the coefficients, it can't just be an abelian group. It really requires an entire coefficient system. Okay, so what do I mean by that? Well, I mean that, I want to be able to evaluate this on GCW complexes. And if I had some G mod H across a disk, well, that disk is contractible. Okay, I have to be a little bit careful to define an equivariant map, but it's not so bad. It should be the same as this thing evaluated at G mod H. Oh, and now I remember why I don't use H for subgroup, because H is cohomology. So I'm going to change my subgroup to K. Forget that every time. Okay, and so the point is I need to know the values on all of these orbits, but also anytime I have a map between orbits, G mod J to G mod K, well, then I should have a map back in cohomology. So I need the data of this cohomology theory on all of the orbits and also the maps between them. Okay, so what I actually need is a whole coefficient system, which is going to be an additive functor. So we get a contravariant functor for cohomology's sake from the orbit category to abelian groups. And this orbit category has objects that are G-sets and equivariant maps. Let's make those finite G-sets. Okay, so these are equivariant maps between them, and they're generated by the orbits. So you can just think of that as just being all the orbits, and then also together with disjoint unions. So it's an additive category. Okay, so moral of the story, already things have gotten a little bit more complicated. Even just to define an equivariant cohomology theory on GCW complexes, I need some extra data. Okay, but then this isn't so bad. So to compute Bernoulli cohomology, what do? Basically, you build a GCW complex. So you say what the cells are and the attaching maps and make those push out diagrams. And then you apply your coefficient system. So anytime you have an orbit cell, you say what was m's value on that orbit. So you apply m to your orbit cells. Okay, and then you also have to keep track of the attaching maps. And then that's going to cook up some cochain complex, and you want to take homology. Okay, great. So that's not so bad. Okay, but now actually there's a lot more here before
Clover,
I get to see a question.
Clover, there's a question, yeah.
Yeah, so does G have to act transitively on finite G sets in orb G? I don't know off the top of my head. I want to say that doesn't seem like an issue, but if anyone wants to jump in, Jeff is suggesting that that's not an issue once you take disjoint unions.
Right, a disjoint union of two finite G sets is not transitive, right? G moves them over here and G moves them over here.
Yes, excellent, thank you. So yeah, I don't want to require that. Just finite G sets. Okay, great. And someone pointed out that if you assume that M sends disjoint unions to direct sums, I said it's an additive functor, right? Then you're all well and good. So great. Okay, so this is a fun thing to do. You can start computing Bernoulli equivariant cohomology, but you've probably heard of fancier equivariant cohomologies. And what is that all about? Well, the idea is that really there's a lot more stuff going on in this category, sort of behind the scenes. So I want to talk about that. And the key idea here is that anytime you have V, some real orthogonal G representation, so you've got some vector space with a G action, then you can take the 1-point compactification and you'll get a sphere with the induced action. Okay, so I'll write that as S superscript V for the 1-point compactification. And this is what I call a representation sphere. I think most people call this a representation sphere. I'll try to warn you when my terminology is not the same as everyone else's. Okay, so we have all of these new flavors of spheres, whereas in the non-equivariant case, my spheres were only sort of interesting up to the dimension that they were. And now there are many kinds of 7-dimensional spheres, and they all have different flavors. They all act a little bit differently, right? So armed with these spheres, I can take the Vth suspension of a space. And what do I mean by that? I just mean take SV and smash it with X. And I feel like most people here probably know what that means, but let me just be really explicit. in case you don't. So I just mean take the product, and that's G acting on that diagonally, and then mod out by the wedge. Okay. Okay, and so now that we have all these interesting flavors of spheres, we can talk about the V suspension. Well, one of the things the cohomology theory has is a nice suspension isomorphism, and I might want a nice suspension isomorphism with respect to these new weird spheres, right? So Berdan cohomology has a good suspension isomorphism with trivial spheres, but not necessarily with these things. And so what we need for that is an ROG graded theory. And this is where ROG comes into the picture. So ROG is the Grothendieck group of real orthogonal G representations. Trying to make this so you can read it, but let me know if there's anything you can't read. So I have this Grothendieck group of real orthogonal G representations, or you could just think of this is the group made by the representation ring. I just don't really care about that ring structure. Another way to think about it that's convenient is to sort of think about it as having a basis. So this is the free abelian group on irreducible representations. Okay, so how does ROG really come into play here? Well, the key connection is this theorem due to Lewis, Peter May, and McClure. And it says that this ordinary integer graded cohomology that we had before, so Berdan's cohomology theory, well, this extends to an ROG graded theory. Well, not quite always. So it extends to an ROG graded theory if and only if, maybe let me call it an ROG graded cohomology. That's what I mean by theory. Okay, so if and only if M, our coefficient system, extends, well, let me call that coefficients M. I need this to extend to something called a Macufunctor. So I imagine that some of you are familiar with Macufunctors, some of you have heard of Macufunctors, but don't really know what they are, and some of you are hearing about this for the first time. So I'm going to say more about that in a moment. But there's kind of a little bit to unpack here. So what I'm saying is that we had this ordinary integer graded Berdan cohomology. It was graded on dimension, right? Dimension of spheres in our usual cohomology sense. And now it's ROG graded. So that means I take some alpha in ROG. Well, that's a Grothendieck group of real orthogonal G representations. So this is some sum or difference of isomorphism classes of actual representations, right? And what I get from that is something that looks like H superscript alpha. I'll decorate it with a G because it's still equivariant. I take cohomology of my pointed G space, and now I need coefficients in a souped up coefficient system. So I still have to tell you what a Macufunctor is, but that M underline is going to be a Macufunctor. And the point of this is that this is, they prove this is a nice theory and everything works out in a lot of nice ways, maybe not all the nice ways you might hope for, but one thing we do get is a good suspension isomorphism. So what do I mean by that? Well, if you looked at the reduced cohomology, the reduced alphith cohomology of something, you could compare that with the reduced cohomology of now the Vth suspension, right? Smash with a V sphere. And normally what does that suspension isomorphism do? It just shifts the indices, right? If I was smashing with an N sphere, I should add N. So now I should take that and add V. And now you can see why I don't want to just grade on representations, but I really want to grade on ROG, because if I had started maybe over here, just thinking of this as some beta, right? Then I'd want to be able to subtract V to get over to here. So I need to be able to add and subtract representations from the grading. Okay, so that explains a little bit about the grading, at least that it's there and how we're going to indicate it. Maybe let me say one more thing about this theory before I turn to Macufunctors, which is that one reason you might want this is this has a good, and they prove this, that you get a good Brown representability theorem. So if you had cohomology with coefficients in a Macufunctor M, and I really want to vary that alpha now, then these cohomology theories are represented by genuine equivariant spectra. Let's say a genuine equivariant Eilenberg-MacLane spectrum. And I'm not really assuming that you know what that is, so I'm kind of just saying this. If that means something to you, I'm not going to dwell on it, but the point is there's a nice spectrum representing this cohomology theory. Someone asked, what precisely does it mean that it extends ordinary Berdan cohomology? And that's a great question. So let's go ahead and write that now. So if alpha is if this thing is n-dimensional and trivial, then my H alpha is the same as Hn, the Berdan cohomology. So that's what I mean by extends. The trivial representations have Berdan cohomology already built inside it, but now we're also going to extend to non-trivial representations and allow those to be in the grading as well. Okay, cool. So well, I've written M underline a bunch of times now, and I haven't told you what a Macufunctor is. So I said it's kind of a souped up coefficient system. And if you like, you could sort of ignore the technical details of what it is, but I imagine that some people have been told to ignore it before and are itching to know. So let me give you one definition of a Macufunctor. I think I know at least 3 equivalent ones. And I won't even say this is my favorite one, but it's the shortest to write down. So we'll start there. I think it's Webb has a great guide to Macufunctors if you're looking for a reference. So, well, we already know that we should have a contravariant functor, contravariant additive functor from our orbit category to abelian groups. And so we do have that. But what's strange about a Macufunctor is that we also get another covariant functor, and that these are compatible in certain ways. So I'll spell that out in just a moment, but it's kind of this extra data. So I'm going to get these wrong way maps called transfers, these things that are covariant. When I was working with a cohomology theory, everything should be contravariant. So what are the things that we need here? Well, the first one is that they're compatible in the sense that they take the same value on any finite G set. So T is some finite G set here, and the upper star and the lower star, the covariant and the contravariant part, take the same value, so I don't usually even decorate it. I just call it M of T. The second one is that the contravariant part preserves products. And then the third part is really a kind of strange and deeper compatibility that we need between these things. So this is sometimes called a push-pull formula. But let me spell it out. So what I want is that if I have some pullback in finite G sets, and I'm actually going to label the maps here, then I can apply the Macufunctor. Well, I could apply the contravariant part or the covariant part to get the same thing on each of the G sets. So I'll just write M of P, M of R, and so on. But now what I'm going to do is something that at first I think felt very strange. And that's to combine the contravariant and the covariant parts. So that's what makes this push-pull. So the vertical maps, I'll apply the contravariant part of the functor. So this is like G upper star and I upper star, and then I'll use the covariant part at the top and bottom. So I am liable to make mistakes about the direction of arrows and things like that. So you should be careful, but in this case, I mean it. These really do, this is a commutative square that looks kind of funky, right? It didn't turn into, it didn't stay a pullback or become a push out. Okay, so someone asked, do you mean that M star preserves products? And yes, I do. So it should be an additive functor, but I can take T cross S and get another finite G set. It's going to decompose into a disjoint union of a bunch of orbits, right? But I can also think about that product structure. And so I really do mean to think about the product. Oh, the question was actually about M upper star versus M lower star. That I guess I'm less sure about. So maybe let me make a note. Check. That's what I have written down, but off the top of my head, I don't remember. Okay. Great. So a Macufunctor is this weird set of data. Like I said, there are multiple definitions, but this one is short to write down, and at the very least, it kind of gives you the sense that these wrong way maps have to have these nice compatibility with the maps that we had before, but it's a little bit weird. So what I want to do now is take all of this kind of high level theory that we've been looking at and try to make it a little bit more concrete, specialized to my favorite group, and look at what we get there. And we'll unpack this definition a little bit in that setting. Okay, maybe I should leave that formula in case people are still writing. So now let's let G be C2, the cyclic group of order 2, and we'll probably stay here for the rest of the time. Though maybe I'll make some comments about other groups. So the first thing we talked about was GCW complexes. So what kind of orbits do we have here, and what kind of orbit cells? Well, we've got C2, which I can think of as C2 mod the trivial subgroup. I've got a point, which I can think of as C2 mod C2, so just 2 orbits. That gives me 2 kinds of orbit cells. So C2 cross a disk and a point cross a disk. I don't know if you can hear my cat, but she's very upset that I'm not playing with her right now. We may get some cat interference. Okay, so what do these look like? Well, this is just doing a point cross something, doesn't really do anything. This is just a fixed disk. But C2 cross a disk, that means this equivariant cell really looks like 2 disks, and the C2 action is swapping them, right? So, okay, and maybe just to actually build a space, though we'll do a lot more of this next time, let me build something. So for example, I could take a single point, and then I could take C2 cross a disk. She has this habit of unplugging my computer, so hold on a second. The joys of working from home. Okay. So I'm going to attach this C2 cross DN along its boundary, which is C2 cross S1, right? Sorry, I should have drawn a little swapping to remind you. Okay, so I want to attach that along its boundary. And the way that I'm going to do that is, well, there's not a lot of maps, so I'm just going to crush everything. And that's going to form this wedge of 2 spheres. But notice that they're swapping. So all of that, those S1s got crushed to a point, and that point's fixed, and then I'm just swapping across that. Okay, and someone asked, is the push-pull axiom related to the double coset formula? And yes, if you've seen the double coset formula version of the Macufunctor definition, that is all packed in there. That's why I like this one, it's short. I don't have to say that. There's another version that I prefer, more involving the Burnside category, which is like a souped up or maybe stable orbit category. but it all takes longer to say. Okay, so we've got a C2-CW complex. What kind of representations do we have in this setting? Well, remember that we have to think about real representations. Just eating some chords. My cat's name is Bianca, by the way. You'll probably meet her several times during this. Okay, so I've got two irreducible real representations, the trivial and the sign representation. And so any representation here, I'm going to write as some RPQ, by which I just mean a bunch of copies of trivial and a bunch of copies of the sign representation. Okay, but the indexing is a little bit funny, so I'm going to take Q copies, make sure that's readable, Q copies of the sign representation and P minus Q copies of the trivial representation. And if you're familiar with motivic homotopy theory, then I'm using the same grading convention there. One of the challenges in this theory is that you look at different sources and people use different grading, so you have to be a little bit careful. Someone asked, can you provide an example where we don't have fixed points by the action? One could be like the sphere with the antipodal action. Yep, that's a great example. Also C2 itself is a C2 space, right? That doesn't have a fixed point. But remember that we're going to ultimately want to work with based spaces. And so we'll just add a disjoint base point when that happens. Okay, good. So why am I setting things up this way? Well, one, it agrees with the motivic world, but the motivation here is that P tells me the dimension, so I can just read that right off, these sum to P, and Q is the twisted dimension, or sometimes it's called weight. And P minus Q is the fixed set dimension. So sometimes people prioritize that and make that part of the grading. I've also seen this recently called co-weight. So you might see that. Okay, and then that means that when I take the 1-point compactification, well, I get a representation sphere, but I could really just think of this as a bigraded family of spheres. So I'll just keep track of P and Q. And now P is the dimension of the sphere, and Q is the twisted dimension of the sphere. So maybe let me write. Now P becomes the topological dimension, and I like being able to read that right off. So let's look at some examples. Because I want to make this very concrete and have lots of examples in mind, and these things will come back later. So let me just draw a few. Okay, so the first one will be S10. So I take, what am I supposed to do? I'm going to take one copy of the trivial representation and 1-point compactify, and I should say the base point goes at the point at infinity. But, okay, that's not very interesting. I get a trivial circle. If I take one copy of the sign representation and 1-point compactify, then I get, well, okay, I have this reflection action, and then 1-point compactify is reflecting, reflecting, reflecting until that point at infinity collides, and so that's a fixed point. So I've got these two fixed points, the origin and the point at infinity, and this is just swapping across here. Okay, and let's look at some two-dimensional examples. S20, that's two copies of the trivial representation. Again, trivial action on a sphere, so that's not maybe too interesting. If I take S21, so I have one reflecting copy, one copy of the sign representation, then I'm going to get a reflection action on my sphere. So reflecting across the equator, say, and if I take two copies of the sign representation, so I'm reflecting in X and I'm reflecting in Y, that means that I'm rotating in the plane. And so when I 1-point compactify, I'm going to get this rotating sphere. And so I'll just have that origin and the point at infinity fixed. And this is like a sphere rotating around its axis. So I'm going to give you some homework for next time that is hopefully fun. So find C2 CW structures we're going to want to be able to decompose these things. Find C2, CW structures for some of these spheres. You could do all of them if you want, but at the very least do S11, S21, and S22. Okay, and then again, notice that first number is telling me about the dimension. So I had a bunch of 2 spheres here on the right, and the other number is telling me about the twisted dimension. So when I say find C2, CW structures here, you're going to want to find cells and attaching maps. Orbit cells, right? Okay. Trying to keep an eye on time here, but let me at least sort of motivate a little bit more why we need this Macufunctor structure before we end. So notice that we have a map from C2 to a point. I can just crush everything, right? And I have this C2 acting on itself, this twist map. And so I could build my C2 CW cell complexes using the orbit cells and then also these attaching maps. I'm not drawing the identity maps. But so what that gives me is that I have a map from C2 plus smash a sphere to a sphere. I'm drawing this as a representation sphere. I could write SPQ, but this works more generally. So I've switched back to B. But I can think of that SV over here as point plus smash SV, right? If you smash with S0, you haven't done anything. Okay, and there's an obvious map here. Just do that same crush. So here I have these 2 swapping spheres, and I fold them onto one. Okay, but the Macufunctor structure gave us not just those maps, but also these wrong way maps. And one of the ways that we can see that we would need those is to think about going the other way. So is there a map from SV to C2 plus smash SV? Well, there isn't a map from a point to C2, right? There's no equivariant map because the point is fixed, but there is a map once you smash with a representation sphere. And again, I said this works more generally. I'll just say it in this context, but the same idea is going to work. So I take my representation sphere, and I'm supposed to somehow get something that maps to these swapping spheres. And what I'm going to do here is just find that orbit C2 sitting inside this. So maybe this is an S22 and they're on opposite sides of the sphere or something, or maybe it's an S21 and it's reflecting across the equator. And then I should have drawn them slightly differently. But I find a little neighborhood of those and crush outside of that. And that's going to give me a map to 2 copies, and they're swapping because that was a copy of C2 sitting inside, right? That copy was swapping inside there. Sorry, this picture ended up kind of small, so hopefully that makes sense. Let me give you a name here so that you can look this up if you like. So this is just the Pontryagin-Thom collapse map. Okay, so why am I talking about this? Well, the point is, if you do smash with representation spheres, you do sort of get these wrong way maps already on the orbits, right? And if I want to work stably, I should be able to smash with S minus V and get rid of those. Or if we want to think about cohomology, there should be this suspension isomorphism. And so I should be able to also desuspend and remove these SVs and get a map the wrong way. So that's part of why we need a whole Macufunctor here and get all of that data. So what do Macufunctors look like here in the C2 world? Oops. Well, let me first draw that orbit category to remind ourselves. I'm going to draw it vertically so that I can draw a nice Lewis diagram for my Macufunctor. So this is just orb C2. Or really, I haven't drawn all of it, but I've drawn the generators, right? Everything else is going to be a disjoint union of these 2 orbits. And so then my Macufunctor is supposed to have values at each of the orbits. So some m of C2 and some m of a point. And then I should also have contravariant maps for each of those interesting maps. Of course, identity goes to identity. I'm not drawing those. And that so far, what I've just drawn is essentially the data of a coefficient system here. Though there's a little bit of compatibility that you need. But a Macufunctor also has this wrong way stuff. I should be able to go from C2 back to a point. And so I also have a P lower star. And it turns out T upper star is the same as T lower star. And so I usually just call it T in this particular small case. But larger groups, it could be more complicated. Just in case you're looking at other sources, this is also called the restriction from C2 to E of P, and the lower star is also called the transfer from E up to C2. Okay, but the Macufunctor that we're going to be, yeah, okay, wait, let me say that in one moment. So an exercise in playing with this push-pull formula is to check that one of the funky relations that you get is that P upper star after P lower star has to be identity plus twist in this Macufunctor. And there are some other relations coming from the orbit category. Those ones aren't so weird, but the Macufunctor we're going to be interested in will be the constant F2. So constant just meaning put F2 everywhere. And also meaning sort of do the, I don't know, I want to say the sensible thing on the contravariant stuff. Who knows what's sensible at this point, but make all of those restrictions identities. So all your upper star maps are going to be identities. So just multiply by 1, or yeah, multiply by 1. Okay, and then this formula here is going to tell me that if I went here and came back, that it should be 1 plus 1, which is 2. But that's 0 mod 2. So this map had better be 0. Okay, so I get some sort of weird constraints here on the maps. But this is the constant Macufunctor. And this is mainly what we're going to be working with. So remember, we had these bigraded spheres. We had these bigraded representations. So ROC2 is bigraded. And what we're going to want to work on is computing this ROC2 graded cohomology of some C2 spaces with coefficients in a Macufunctor. Well, I'll write that as HPQ since it's bigraded. And I usually leave off the C2, we'll just stick with C2. So that again reminds me of the dimension of the spheres and the twisted dimension. And in fact, let's just work, at least for now, with this constant Macufunctor. This is sort of like the easiest coefficients you could think of. Well, maybe that's not entirely true, but non-equivariantly, working with coefficients in F2 as a field, everything's pretty easy there, right? So I would want to start here. Okay, so let's do that, and I'll even leave off the coefficients in most of what we write. So we're going to be, the upshot of all of this sort of theory we've been working on is we're going to be computing this bigraded cohomology of C2 equivariant spaces. Okay, and if a lot of that stuff didn't make sense, that's okay. You can still jump back in because we're really only going to need certain data from this. But the goal that we're after here is to learn how to compute things like this bigraded cohomology of X. Okay, and maybe I should check in with Dan. How much time do I have left? Should I keep going or should I stop here?
Well, it's your choice. I think we should finish by 12:30 or 9:30 or whatever time it is for you, for sure. So find a good spot between now and then to wrap it up.
Okay, I think I can say a little bit more then. Okay. So someone asked, how does this relate to Berdan cohomology in the more general setting? And let's make sure we see how that relationship works here. So the first example we'd want to know is the cohomology of the easiest space you can think of, a point. It's got a trivial C2 action. Let's try to compute it with F2 coefficients. And the Berdan cohomology of this thing is just HP0. So remember that came in for our trivial representations. So this is Berdan cohomology. And we know how to compute that. So we can at least compute some of this. So let's get it started, and then we'll come back to it next time. But what do? We build a C2 CW structure, and then we're going to apply our coefficient system, or our Macufunctor, F2 underline. So if we wanted to compute HP0 of a point, well, what do we get? There's an easy cell structure. It's just a single point. I meant that dot to be a point, not a bullet, but maybe let me write the word point to make that really explicit. Okay, so I apply my Macufunctor, my coefficient system, and well, this took the value F2 everywhere. So I just have F2. And of course, there's no higher dimensional stuff. So everything else is 0. And there's really no interesting maps. So this is like in degree 0, in degree 1. Of course, I don't need any 1 cells to build a point. I don't need any 2 cells, and so on. So what do I have? I have an F2. I can take cohomology of that. I have an F2 in degree 0 and 0 else. Okay, great. That makes sense, right? The cohomology of a point, it should just be an F2 in degree 0. So, so Bourdon does give that to us. We'll see that the ROC2 graded cohomology is quite a bit more complicated. Before we do that, let me also say we had another orbit. So what if we wanted to compute the cohomology of C2? Okay, if you like, C2 is not pointed, so I could give it a disjoint base point and do reduced cohomology just to not have extra stuff around. I'm just going to write it as this and not worry about the disjoint base point for a moment. So same deal, easy cell structure. I should just have C2. I have these 2 swapping points, and I apply my Macufunctor. So F2 underline applied to C2, well, it's just F2, and 0s everywhere else. Okay, and again, easy to take homology of this complex. So same deal. I have an F2 in degree 0 and 0 everywhere else. Okay, so that's maybe a little bit disappointing because Bourdon cohomology gave us this nice answer for the cohomology of a point, but it also can't see the difference between C2 and a point. Okay, I'm kind of lying. I could have used a different coefficient system or a different Macufunctor, and I would have been able to see the difference, but it's reasonable that in F2 coefficients, you lose some data, right? And so in this particular case, it can't see the difference. Okay, but what's weird is, before I scroll past this, so what I really want is this whole bigraded thing, right? HPQ of a point. And now I only know how to handle the case where Q is 0. So that's Bourdon cohomology, and I know what to do there. Where it starts to get weird is for Q not equal to 0. And the short answer is you get a lot of wild stuff. You think you should get the same answer. It's the cohomology of a point. It should be pretty simple, but you actually get a lot of stuff. And I tried to, oh, nope, I copied and pasted already. I tried to cheat and have this picture saved in memory, and I erased it. So let me draw it. So it's bigraded, so I'll draw a bigraded picture in the plane. And I'm gonna let a dot stand for an F2, and we just computed essentially the picture on the p-axis, right? So we know that we should have just a single F2 there in degree 0. But as soon as you get away from the p-axis, you get a ton of stuff. So there are 2 dots there. There's 3 at the next level, 4 after that, and so on. So there's a whole bunch of stuff. And then there's a little bit of a gap here, but in weight -2, again, you get more stuff. Okay, and I won't draw all of it, it goes on forever, but let me at least kind of try to tie this together. So maybe you've seen this picture with 2 cones before, at least if you've seen me give a talk. So this is, what I'm drawing here is what I would call M2. And this is the bigraded cohomology of a point. And I said we'll always use F2 underlying coefficients, but let me just write it here to be really explicit. So we've only learned so far how to compute this single dot, but there's a ton of stuff here. And let me just say, we have this polynomial kind of behavior in the upper cone. So it's polynomial in rho and tau. And then there's this element theta in weight minus 2 is divisible by rho and tau, and really infinitely divisible. So this goes on forever. So we have a bunch of F2s. And what I mean by that last statement is that like theta over rho, I multiply by rho and I get theta. And the upshot, where I'll end here, is that this is an infinite dimensional non-Noetherian ring. So this is part of what people mean when they say that equivariant cohomology computations are hard, because you take the easiest space and the easiest coefficients and you get this giant infinite dimensional non-Noetherian ring. It is commutative, so here I had rho tau, and that's also tau rho. I didn't write it down, but you basically like can't help but start with a mess, I guess is what I'm trying to say. So part of what I want to do in the next lecture is learn to compute some more complicated things. I mean, we did some pretty baby cell structures here. There wasn't a whole lot to do, so look at some more complicated things, think about Bradan, try to understand a little bit where all this extra stuff is coming from, and also just use this data to now compute cohomologies of other spaces, because their cohomology will always be a module over this, since there's always a map to a point. So I'll come back and say that next time, but let me stop there.
Okay, terrific. All right, thanks very much, Clover, for the first time.